All right. Well, another day, another stream. So in this stream, as I said, I'm going to be doing uh, you know, a stream in GPU architectures and basically using the Vulkan API. That's going to be the primary focus. Um, so the next or part two of this stream is going to focus on something very, um, I would say it's very important because this is something that I've spent quite a lot of time putting together. And I'll tell you why as well. So let's just jump straight into it. So when you usually, want to learn about this stuff and you go looking around for literature that's available freely, you'll find that the first thing that you see is there's a lot of information available that talks about modern GPU architectures, but the discussion is usually around, they, as I say over here, they straight away jump into speeds and feeds. Uh, Basically, they're talking about the concept of latency versus throughput. So, well, we'll also do the same thing, but uh, we will also look at a very important part, which is how do you actually talk to the GPU? Right? So in the previous stream, we spent some time talking about what the Vulkan API is, how it's different, etc. Now let's look at it from a more, um, you know, look at it have a generic view about things. Let's say it's any GPU and any other uh, GPU programming API, say Metal or CUDA or Vulkan or whatever it is. You know, what's common amongst all of them? Let's look at all of that. So the first thing is, yeah, CPUs. There are. So when you try to compare a CPU with a GPU, you would see that the CPUs are, you know, just raw core count. You'd see that there are fewer cores, but those cores are larger because they have additional uh, things that are built into them, or IP that is built into them to do with things like prediction, branch prediction, or out of order execution. All of that stuff doesn't exist on a GPU. They're mostly dumb cores, as I would call them, but they do, you know, they have a lot of them. The CPUs are fewer cores, larger cores, and faster cores. So clearly, the priority over here is latency. That means they're optimized for doing things really fast. And by definition, that also means they're very good at general purpose computing. It means you can take any algorithm and you'd be able to sort of map it onto this CPU kind of architecture, or what you call a von Neumann architecture. And GPUs, on the flip side of things, as this diagram presents, it's much smaller cores, and that's you'd also see the dimension. This is just a representation. So you'll have smaller but slower cores, and these cores are you have a lot of them. And the goal and the focus over here is it's prioritizing throughput. Means they're designed for data parallel calculations. That means basically wherever you can achieve some amount of parallelism, you'd really want to leverage a GPU for that. Um, the other thing is you'd also see things like caches. So both processors, that's a GPU and a CPU, have caches. And um, the way they're laid out and how much or the size of those caches are very, very important. I mean, they've become very important in the design when we talk about latency versus throughput, that discussion. GPU dedicated a lot of the silicon area for actual compute stuff, whereas CPUs have a mix of both, but they do tend to have larger caches and stuff like that. All right, um, because what they try to do is late. They're not going to be good at latency, so they try to hide latency by pushing out a lot more work. That is a lot more throughput. So that's what you would normally see the moment you start looking at CPU versus GPU discussions. And yeah, that's pretty much what you see over here as well. Then the next thing that you jump into is you'll see a diagram that looks something like this. It'd be like, okay, this is a block diagram of one of NVIDIA's products called the H100. It's not the latest one, but something, good enough. And you would see, okay, there's a lot of stuff going on in here. There's on the left-hand side, you'd see there's memory controllers that sort of help you talk to what is called high bandwidth memory. And there's actually multiple of these. And then you've got these green boxes inside. Each one of them is inside what's called a graphics processing cluster. And then we'll have a zoomed in view as well. And then at the bottom, you also see that, there's a high-speed hub, which basically uses NVIDIA's own fabric that helps you talk to other GPUs. This is the whole multi-GPU distributed parallel computing stuff, not just distributing work within a node, but between nodes and stuff. So you'll see all of that. Oh, so this is great. So far you will be able to get a picture saying, okay, this is pretty much how a GPU works. All right. If you want to know a little more, then you can jump in and say, okay, let's just zoom into one of these little blocks, which is one of these blocks. You'd see that, okay, this is called a streaming multiprocessor. It has a whole bunch of pieces inside it. But effectively, it'll have a very large register file, and it's got a lot of, you'd say, compute units, you can say. Um, so all of this stuff is great. I mean, this is exactly what you'd want to know when you're talking about a GPU, saying how is it that these things are actually so fast and stuff like that. So you'll see that there's a instruction caches, there's a tensor memory accelerator, there's a texel buffer. All of that stuff is great. But when you're starting off, having a high level view of this picture is good. Diving into it uh, straight off the bat is not going to tell you one very important piece. And that piece is what we want to discuss today, which is, you know, how, sorry, how do you actually program the GPU, right? Because there's two parts to this. The way I look at it is one is, when you basically say, I've written some GPU code, it's going to run on, you're going to have multiple threads that will be making use of, a portion of these, you can say cores, right? And you get your work done. So you know how that work's going to be distributed at a high level. That's great. But that's not really enough. That's only half the story. The bigger story is how do you actually program that GPU? And that's exactly where the Vulkan API comes in. So in this case, when we talk about the Vulkan API, we're basically talking about, you know, programming a GPU in the sense that um, how is it that I can get it to do what I want it to do? That means, do I send it a command and it responds to that command? Do I set some register somewhere and then, communicate some intent and then it magically does some work and comes back to you? All of this stuff is what you deal with if you're dealing with embedded systems programming. And lo and behold, it's no different on a GPU as well. So effectively, like if you were dealing with, let's say, you were writing something like a networking driver, all right? Um, you'll pretty much come across the concept of, things like ring buffers, effectively a transmit queue and a receive queue, which is exactly a ring buffer where you want to send some uh, data to the network card that you have or network interface card, and the network interface card receives data that wants to send back to the system. All of that stuff that you do effectively uses some form of um, command response mechanism or communication method. And the GPU is no different. Effectively, underneath all of this is the core part that actually runs your GPU code and what we call shader codes, etc., they're all great. They will do the actual work, but there's something that's actually going to be orchestrating all of that. And that's what we'd call a command processor. That's sort of a tiny microcontroller or a much powerful microcontroller, depends on what kind of GPUs we're looking at, that are baked into the GPU itself. And basically, GPUs operate on what's called a command response model. So you send it a command, and once that command is processed by the GPU, it notifies, in this case, the application that's made that request that, I'm done. Here's the response. If, there's something to show or something to return back to the application. So effectively, when you explore the Vulkan documentation, you're going to be looking at terms like commands recorded into a command buffer, commands are added to a command queue. What the hell is all of this? Is the first question that will pop into your mind, because the moment you start looking at the API and you try to understand some pieces, you'll get a few things. That means a few things may click, but unless you know at least the very high level view of how do you program a GPU, uh, things tend to be a little hazy, right? You don't know who's exactly doing what and how should I be thinking about this. Um, so this is good for a mental model, and that will carry forward. And I'll sort of allude to that as we go along. So the first thing is, well, how do you program the GPU? You use the CPU, which means you write your commands. That's what we'd called command construction. And then you record those commands. You record those commands and then you submit those commands to a command queue. And that command queue will be looked at by this thing called the command processor on the GPU. It picks stuff from there and says, okay, I have this command. I'm going to go ahead and do the work. And I've put together, and this is the thing that took me a while to sort of put together, because I'm I find it really hilarious that none of the GPU vendors think this is important enough. Just a simple high level view of, the pieces involved. Let's say I'm an application, I, send a command. What are the relevant um, software pieces? Let's just say, what are the software components that are involved in this? What does that look like? And this is sort of what it looks like. It's a very high level overview. And there's a whole bunch of pieces that we'll get to as we go through this entire series. But effectively, your application is the thing that you will be writing, which I'll be showing you anyway. Um, and as I said, Vulkan is the API, the GPU programming API. That's an explicit one. It's a pretty low level one. Gives you direct control over the GPU and its resources. You can pretty much turn any knob that you want to suit your needs. So that's usually what you'd call a vendor runtime. The vendor is because there's a lot of proprietary implementations as well. Vulkan is the open source one, right? OpenGL used to be the other one, but that's not finding a lot of support. I'd say that much. But it's still used quite a bit because there's, I don't know, 30 years worth of OpenGL stuff out there, right? Then once, so the application sort of relies on the vendor runtime, and the vendor runtime sort of interfaces with the driver. I talked about the driver in the previous session as well. I said, where was that? Yeah, I said something like this. There's an application, we do all of the Vulkan runtime stuff. And then there's what's called an ICD, which is basically an installable client driver. In this case, that's basically the user space component that you see over here. Okay, that's it. So this stuff is what's going to take the commands that you've constructed, translate them into the hardware specific, the GPU specific commands that they need to be in whatever format that is. And then there's usually a split. In all modern GPU software architectures, there's a split between the user mode and the kernel mode, because the user mode does some stuff, the kernel mode does some other stuff. So it's good to have separation. Also from things like a security safety standpoint as well. Uh, yeah. So there's another question that you would probably have. I mean, if this is all we need, why the hell do we need an operating system, and why do we need it to have something for Linux, etc.? It's a very good question. I'll come to that later. Um, then, so once those commands are sort of translated into hardware-specific commands, they're passed off to the kernel mode driver, which operates at the kernel mode, which is a privileged level from user space. Um, and there, that the kernel mode does a bunch of things like GPU device initialization, things like managing hardware interrupts, memory management or resource allocation and stuff like that, because you don't want multiple applications to sort of be, managing their own memory and, doing whatever the hell they want to do. So you sort of want some guardrails around that, and that's that's the job of the kernel mode driver. Finally, what happens is the commands that you've crafted, you've translated, and all of that, they're passed off or they're submitted or inserted into something called a queue. Now, the idea is the queue is nothing but a ring buffer. And I'll sort of talk about what a ring buffer is. It's a buffer. It's like an array, except that um, conceptually it, it looks like a circle, but it's not a real circle. There's no circular memory physically in a machine. It's just basically saying that, there's a read pointer and a write pointer. They sort of wrap around whenever they are done filling the buffer, sort of wrap around, go back to the front. Then you keep going through that cycle. So you just have a buffer that you keep overwriting over and over and over again. That's the simplest way to think about it. And this ring buffer that we call, the way we talk about it, is basically shared memory. This is memory that exists on your um, on the CPU side of things. This is your system memory, that is your main RAM, and it's sort of mapped to uh, your GPU as well. So your GPU also has direct access to this. That's the way these things are set up. And the GPU command processor actually picks stuff from that queue. So the application is writing commands to that command queue, and the GPU command processor is picking commands from that command queue and basically pummeling through that queue, finishing work that's been queued up or enqueued. Right? So it reads, decodes, and executes the command in the command buffer. This is the high-level picture, and I think this applies to pretty much every API. That includes CUDA as well. Uh, this is how things work, is what I understand. Unless somebody who watches this and is, you know, uh, knows that I made a mistake of some sort. I'm pretty sure I'm not, because I've actually verified this by writing some code. So, but you never know. Okay, I'm still, you know, it's always something, little pieces that you may miss. But I'm assuming that at a high level, this makes sense. Anyway, so that's the first thing. The second thing I also want to talk about is, I told you that, okay, you submit a single command, it goes through this entire flow, and then the GPU command processor does its full thing, and you're done. But these are two separate processes. The CPU is a separate one, and the GPU is a separate processor. How do you know when you're done with the work, right? How does the CPU know when it's done with that work? And that's where you bring in the concept of synchronization. And synchronization for today, I'm only talking about host to device, as Vulkan refers to it. Notice they don't say CPU to GPU, because device and host can keep, you can flip them around. Sometimes, I don't know, you may have a CPU that can also be a device, um, depending on the terminology, etc. But in any case, I'm right now only talking about CPU to GPU. So what happens is, when you write your applications, you can use things like fences, semaphores, events. These are all synchronization primitives that Vulkan offers. Nothing fancy. It's basically, you're going to write to some, you're going to set a flag in memory somewhere and say, okay, let me know if this state changes over here. And then the GPU sort of reaches out and says, okay, I'm done computing. When I say the GPU, I mean the command processor, because it knows, this command has been completed. So I need to, the application has asked me to sort of notify you. So I'm going to do that. All right. So that's basically called what we call, uh, there's another command that goes along in the command stream itself for that. So here you can see that, you start with you create a fence, and then you set that fence to unsignaled, which is basically 0 or 1 or whatever that is. And then this thing lives in system DRAM. And then you sort of go through that entire pipeline. When you're submitting a command, the fence also goes along with that command saying, okay, if you complete this command, wait. That means till you complete this command, basically I'm going to be waiting. So you need to tell me that you've done with this. So the command processor is basically going to go ahead and handle that and then update that, either depending on how you built your application, whether you're going to be polling for it, which is pretty inefficient because this is called busy waiting. That means you keep looping and waiting for, the state to change. Or you can do something like block waiting. So effectively, when somebody says other than interrupts, if you say blocking wait or anything, it does not mean that, you don't wait. Okay. Your application might not wait, but the kernel driver, you know, yeah, spins something to the side and it does the job of figuring out, how long to wait, etc. But that's just implementation detail. But basically, this is a high-level overview of a very simple workflow in a GPU driver architecture. So yeah, now the reason I'm sort of going through all of this is because when you see the code, it should immediately now make sense. Why are we going through such a long? Why does the code look so lengthy? Why does Vulkan setup have all these pieces in it? Why can't I just send a command and be done with it? Because if you're working with embedded systems, you'd normally see that that is the case. You'd go ahead and figure out what's the wire format. For example, I don't know, I'm just probably working with a crypto accelerator, all right? So those devices are sort of simple, at least for the embedded ones. Um, you send commands to them, they respond, just like a GPU. The commands are much simpler, and the whole process is much simpler. So you exactly know what bytes you want to send, and if you send them in the right order, etc., and you can correctly encode them, etc., you'll be able to fire them off and get them back. The interesting thing over there is those things are not programmable. They're pretty much fixed function units, right? When I talk about a crypto accelerator, you can program them in the sense that you can put your keys and crypto keys and all of that stuff in there, but they're not, there's not logic programmable, is what I mean, right? That's why when you bring the same model over, there's a little more complication, complexity involved when we talk about the GPU, because you have to do all of this stuff. You have many components, many APIs, etc., all working together to effectively give you the most control that you want. All right, so enough talk about these pieces. Just to give you some examples of what the user mode driver is responsible for, what the kernel mode does. We've already discussed this. First thing, the most important thing is translation of Vulkan calls to GPU-specific commands. And then it manages things like pipelines, shader objects, command buffers, all of that stuff that we will eventually get to. The layer stuff that I talked about, which again is somewhere, wait, yeah, right? This stuff, again, all of that user mode, user space driver. So if you see this layer is going to be pretty fat, all right? This one should be thinner and simpler than what you have over here, all right? And then it interacts with the other part. Apart from doing all that work, is it has to interact with the kernel mode driver for things like resource allocation, queue submission, synchronization, stuff like that. The kernel mode, on the other hand, its job is to sort of interact with the GPU. It does the memory management stuff. which is resource allocation and stuff. Submission of buffers ensures GPU security and stability. Uh, this we'll get to. I'll show you what that means. And then interrupt handling and hardware events and all that stuff. All right. So this is a high-level view of what the different user space kernel driver and the kernel mode kernel space kernel driver does. Lastly, there's one thing that, since pretty much most people will work with Linux when we talk about this, GPU devices, the way it's implemented, at least their drivers will be implementing things like open and close, because everything is a file on Linux. And then for stuff, you'll have like 5 calls like open, close, and memory map and stuff like that. And if it's not one of these things, then you just do an IOC2, which means an input-output control. And then you can do whatever fancy behavior you want. That's something that I know a lot of people or different companies would want to see this change. They'd want more, um, you know, a much more standardized way of doing things rather than just use IOPTL for everything else. Yeah. All right, let's come to the command processor, the ring buffer. The ring buffer over here, as I said, is, basically a piece of virtual memory region, which is sort of mapped to the GPU. And the command processor will be able to access that. Physically, that region of memory is actually in the system RAM, but the GPU will be able to access that. And this is why you will be seeing terms like user visible system RAM, or you will see host visible or device visible. You'll start to see terms like this, and you'll be like, the hell does that mean? Well, it means this, all right? It means, can the CPU access, or is a portion of the GPU memory, whatever portion of that GPU memory, is that accessible to the host, and vice versa? Is some portion of host memory accessible to, visible and accessible to the GPU? All right. So this is what sort of goes on. The only piece that I will say is, when I keep saying ring buffer, I don't mean that the entire command that you see over here, whatever commands were encoded on here. Yeah, whatever commands were encoded over here into the system RAM, etc. Those don't, at least in modern architectures, they don't end up in the command queue per se. You actually get a reference or a handle to that command and that command buffer, so that you don't have to, like, multiple applications. If you have multiple applications, you don't end up uh, in a lock contention, because if there's only one queue and everybody has to put all their uh, command buffers into that queue, then you can imagine, you need to have exclusive access when you're writing stuff so that you don't override you know, other command buffers, etc. All that stuff. In order to deal with that, you use what's called an indirect calling method, basically references to other pieces. So, in summary, a ring buffer contains GPU setup and teardown commands, context switching commands, indirect calls to application-specific command buffers. That's, in a nutshell, what a command buffer will contain. And this is just basically system RAM. This is just RAM, okay? And then the last piece I want to talk about, so that these concepts are clearer, is the GPU as a shared resource. Obviously, you have multiple applications that may want to use the GPU for their own computing needs, all right? And it's a job of A, the kernel, and B, the command processor, to sort of work together to ensure that they maintain security, so that if you submit a command, you don't end up, by submitting that command and pushing it out to the GPU, and the GPU sort of trying to call back in some form or manner, accessing system RAM, or different parts of your system RAM, etc. That shouldn't be the case. And that's exactly where uh, the, this is at least everybody thinks that this is a solved problem. people generally on this is on the CPU side of things, they use what's called an MMU. So you use a similar kind of thing on the GPU side of things. That is, you basically have this hardware block called the memory management unit, and then you say any user space application or kernel will have a virtual address space. All right. They don't have a concept of physical memory addresses. That's like abstracted away from them through what's called page tables. I'm not going to go into all that. You can just probably look it up. There's a lot of stuff that you can read up on page tables and stuff. But effectively, the memory management unit, page tables, you'd be able to convert or translate from a virtual address to a physical address. That happens both on the CPU and on the GPU. And then this is what I mentioned when I said the kernel mode driver has this, some job when it interfaces with the hardware. Things like allocating memory regions for the GPU, saying that you can access these regions, and then configuring what's called the IOMMU that's for the GPU, so that it's an IOMMU because CPU is going to be talking to the GPU. So yeah, does the same job, primary job, virtual address translation to physical addresses. And then you set up and populate the GPU's page tables. So all of these page tables are pretty much going to be inside the kernel, all right? That's how you could look at it. So uh, effectively, what does that do? This is used to prevent things like direct memory access attacks. So GPUs have things like DMA engines built into them. That means you don't use uh, the CPU, that is the command processor, to do the transfers, etc. You can go ahead and do it directly. These things are also present on, within what's called an SoC and part of your CPU as well. Same things over here as well. Um, so rather than me talk about it for a long time, I'll just show you stuff. So you have the CPU, let's say it's executing stuff. It comes across an instruction or whatever it is, a memory address that it needs to load from. It only knows what the virtual address is. So it's going to that's going to go to the MMU, and the MMU is going to do the translation along with those page tables. And then it says, okay, this is the page. Same thing happens over here. And that's how the translation happens. So an application need not assumes that it has, a lot of memory because it's all virtual addresses. But effectively, the backing store for that is all physical memory that's done through address translation. Okay. And then I did mention one thing over here. The kernel mode driver is responsible for setting up, maintaining, and updating these page tables. All right. As things change when you're executing stuff, addresses and state and information that's located in that RAM, they need to be updated, and that's the job of the kernel driver. All right. So that's pretty much another detail about, when you're thinking about how does this GPU to CPU, CPU to GPU, use a visible and accessible terms, how do they work? Keep this picture in mind. It will be really helpful. And then there's the command processor. Spending a little time over here, and then we'll finally look at the code. Because once you see all of this, then the moment you get to uh, what you'd call the actual code, it'd be like, okay, yeah, I think I get this. So the command processor over here is also sometimes known as the graphics controller, because obviously it's a GPU. It's legacy naming at this point, I think. I think they should just change the name of the GPU to something called the parallel processing unit. Yeah. Okay. So I mentioned we go ahead and submit commands to a queue, and then this thing called the command processor is going to pop commands off of it and then distribute that or schedule that onto the GPU. What does that look like? Here's what it looks like. So you've got commands over here. Now, this shading may look a little like, misleading, but just know that, these are all references and stuff. The command processor is actually pulling stuff from host memory, the actual bytes, that is. Uh, So what happens is the hardware schedule, this is called and this may not be the same. So each vendor may have their own um, designs for the command processor. And that's another problem, if you ask me. I think you guys should just, all these GPU vendors, it's not rocket science to go ahead and just say you can standardize this process. Because a lot of complexity arises out of here, if you ask me. All right, so the command processor will, at least this is AMD's case, it has a hardware scheduler, and these things are called asynchronous compute engines. It basically takes commands and then the hardware scheduler assigns a command to an asynchronous compute engine. It passes that off to something called the shader processor input. This is where your work, your actual kernel, the programs that you write for the GPU get, distributed to, and they do the work for you. That's the flow. And this particular command processor is actually running firmware. It's called GPU firmware. And that's what people refer to when they talk about GPU firmware. And the other point is you can also see there's something called a memory copy command. So it's not just stuff that goes on to CUDA cores, but you can have a memory copy thing. And this will go not to a CUDA core, sorry, not to a shader core, but it will go to, there'll be probably another unit called the DMA engine. All right, I didn't put that here. All right, there'll be another thing called the DMA engine. And I think I probably have one. Let me just see if I can. Yeah. So you'll have something like a DMA engine over here. This is inside the GPU. You submit that, you go ahead and, invoke this DMA engine, and then you do the transfer into whatever memory that we have. All right. So that's also something that, we could do. And then lastly, one of the interesting things that you see over here is we start talking about, and this will get really interesting as we go down this series, is there's a separation between command recording and submitting that to the queue. You can actually have multiple threads on the CPU do your work. That means record those commands and then submit them to different queues. All right. So that's very, very, very interesting. So that separation allows you to be multi-threaded, multi-queue, whatever it is. You can have many variations and a lot more control over how your application is built. In this case, when I keep saying application, I'm talking about, in general, I'm talking about things like probably building if you're using Vulkan, you're probably building something much more low level, like a compute engine, a game engine, a renderer, whatever it is, right? So yeah, so this is the theory part, right? And now with this context, if we simply were to go ahead and move into the code, everything should be a lot more clearer. Because in the last stream, we talked about the fact that, all you got to do is you've got these, you'll have in Vulkan, you'll have a lot of structs, and each struct is part of an API call. Like if you're calling Vulkan submit command, Vulkan uh, add to queue, whatever that is, okay, or Vulkan synchronization primitive wait for offense, whatever it is, you pretty much will have a data structure that says, okay, exactly what you want to do, and then go ahead and call the API correctly. So we've seen all that. We've turned on debugging as well through this debugging utility. And we've seen all this. So I'm not going to repeat this. You can just see the previous one. What I want to talk about is effectively, we're going to do one simple thing. We're going to go ahead and send a single command. Okay. Just so that we understand clearly how this command is crafted, constructed, translated, and sort of pushed out. I don't think we'll be able to see the translation part. That's the wire format. I don't think we'll be able to see that. Yeah, I don't think we'll be able to see that. But at least let's look at the flow. That means we send the command, we wait for the command to be processed, completed, and for the GPU to sort of report back. And then we look at the response for that. So the way that works is, as you saw previously as well, we enumerate the physical devices that this machine has. I'm working on an M1 Mac, so it only has one GPU because it's all built in. We've seen this. And then the other thing that I'll start off with is once I'm going to start looking at when I go ahead and enumerate the number of physical devices, I'll probably get one because I picked the first one. There's no point looking at anything else. You'll only get one. Um, in other cases, you might get more than one because you might have integrated, dedicated, multi GPU, whatever that is. We're not sitting in that. Then I created an instance as well. So you saw that in the last one. So I can use that to go ahead and start, building my application. So I can use that to query how many device queue families I have. Now, this is very interesting. So let me actually do this first. Let me actually run this because since I've already done this, if I simply run it, I'll talk about the entire output. But before that, we've seen all of this. We've seen, extensions. We've seen what the device is. You can look at the previous stream for that if you're just seeing this for the first time. But here's something that you will see. In the GPU that I actually have an M1 Max, as you can see. Where is that? Yeah, I have an Apple M1 Max. It actually has so the first thing you want to do is you want to go ahead and figure out the queue family type. That means what kind of queues do we have? Is my device supporting, right? So my device is supporting 4 types. That's why the queue family part comes in, and they're indexed 0, 1, 2, 3, which means I have a total of 4 different family types that I can support. Within each family, I have, if this was 2, I'd have 2 of these type, this type. Effectively, this particular M1 Max has the same type of queue, but it has 4 of them, right? And you're just calling it, family index 0, family index 1, family index 2, family index 3. And now you should begin to realize, okay, why 4 of the same, but why are you indexing them? Why can't you just call it queue count 4 over here? You could do that, but you might want to separate your workload very differently, etc. And for those reasons, this may be useful. Also, the way you write your command processor firmware and the way you manage stuff, these things may be important, right? So anyway, long story short, this is the queue families that you need to get. You need to figure out what types of queues you support and how many of those queues you have. And then every time you submit a command, you can have a timestamp to it, and that's the validity bits for that. What kind of queues can be submitted? Graphics, compute, transfers, memory transfers, stuff like that. All right. So that's the first part. Now we're done with that. I'm going to sort of quickly run through this so that I can sort of keep it short. This, by the way, this thing is up on GitHub already. So you can do this at your own leisure. You don't have to watch this with me. I'm just going to explain stuff. So once you know the queue that you want to use, I'm saying I want to use the queue family index 1, the queue type 1, and I'll give it priority 1. Priority I will get to later. There's more stuff that you probably need to know. Again, you see the same pattern. Device queue, create info. So you want so Vulkan gives you this ability to express exactly what kind of a queue you want, what kind of a device do you want, what extensions must be enabled, and all of that. So you do that, and you go ahead and ultimately, once you put all the supporting structs together, you want to create a device. This is the logical device, and that's why I mentioned that up here. You want to handle to the physical device, the logical device, and the queue itself. That's what we do over here. We get the device and we get the queue. These are all handles. Once that is done, then the next thing that I want to do is I want to allocate a buffer. Here's the thing. Vulkan does not provide you an allocator off the bat. You do have something that you can use from Vulkan if you want to. There is a Vulkan allocator. That means I'm talking about a memory allocator. By the way, if you've noticed, all of this stuff is not GPU code. And none of this is actually. This is all being done on the CPU. This is going to be running. That means all the command crafting is happening on the CPU, right? Just keep that in mind. So you might be wondering what's happening on the GPU, what's happening on the CPU. This is all CPU code, right? So I used what's called the GPU allocator crate. This is a pure Rust crate written by Savers Research. Excellent crate, if you ask me. Um, we will explore it further. But you use that allocator to basically first create the allocator. That means you need an allocator before you can allocate something. So you get the allocator, and then you use the same method of the type of buffer that you want, etc. I want this to be a transfer destination buffer. That means I want to be able to transfer things into it. It should be a destination for my memory copy transfer. That level of granularity is what you can specify. And I want 1024 bytes of that. Then there's a bunch of things that called memory buffer memory requirements. I'm not getting into that, but it's important. And then you go ahead and allocate. Once you do an allocate, you get an allocation. This allocation is a physical memory allocation. In this case, I'm allocating some memory on the GPU. So this is stuff that I'm writing that'll get compiled and run by the CPU. But ultimately, we'll be using the Vulkan API to effectively go ahead and allocate memory on the GPU. That's what happens over here. And then we're saying, basically, we want a very specific kind of buffer allocation because we want to be able to read back from the GPU memory. And this is important because in the GPU, you've seen there's caches, memory all over the place. There's very specific areas of memory that the CPU will have access to. You can't just go around accessing everything, right? That's another thing. So you want to be very specific about that. And in this case, I'm not going to write the allocator at all. It's all managed by the GPU. Sorry, by the allocator that you just used, which is a third-party allocator. And then once you're done with that, the buffer that you've created is a handle. The memory that the allocation that you've done is the actual allocation. You have to bind them. This is where the binding piece comes. And you will see a lot of this binding stuff. That means you're binding resources, bind descriptors, bind this, bind pipelines, bind that. All of that stuff is you do some allocation somewhere and then you want to bind it to some reference handle. And that's what all of this stuff is. And then finally, again, once you've done, so you've got your buffer handle, and then you want to go ahead and do your command pool. So this is another case where, so the idea is, as I said, a command buffer will contain commands that will be submitted to the queue. You don't submit a single command generally. In this case, yes, we are. Okay, this is an experiment. This is an example, right? But generally, you'll have a lot of commands in a command buffer and you'll submit them. So what you want to do is you want to first, create a command pool, then start allocating command buffers in there. And then after you allocate command buffers in there, then you start, using those command buffers to include your commands and the resources, the links to the resources that they need, or the references, the resources that they will be needing. In this case, I create the command pool. I say I only need one command buffer in that command pool because I'm only going to be using one command. And then this is going to be the primary command buffer. There's two kinds. We'll talk about that. And finally, I have a command buffer. Great. Now, once I have a command buffer, I can go ahead and start recording my command into it. This is the part where, you saw the user mode doing stuff. It's going to do fancy stuff over here. So the other thing I want to say is, if you notice, device is kind of important. It's going on, you're using device, the handle to the device, to pretty much create all these resources and call all these APIs and stuff like that. So instance and device are two very important abstractions that are provided to you. Pretty much every API provides them, right? At least every explicit API provides them. So coming back, so you've got your command buffer from a command pool. You also got your buffer that's tied to the actual allocation. Now you want to go ahead and start recording your commands into that, right? You're not actually recording, your data and all of that stuff. You're recording a command. The data can be provided, as a reference to it. So go ahead, do this thing, but here's your data. That's how you would think about it. So the command over here is called command fill buffer. This is just the memory transfer operation. I want to be able to write 4 bytes in a repeating pattern into that 1024 bytes that I just allocated, right? That's what I want to do. I want to write this particular value. That's it. So I start recording the command and then I end it. That's very important. So begin and end is when you stop. Once you do that, then you also create this fence. That's what I talked about, which is this synchronization object that you create. It's just a slot in some memory, in the system memory. And you're going to say, okay, go ahead. And once that object is created, you want to go ahead and say, submit this along with the fence. That means once you complete this command, I want you to notify me. Don't go ahead and process more commands without notifying me about this. That's effectively what you're trying to say over here. And then your job over here in this thread is you're going to continue. You'll submit this, and the whole thing about the GPU is it's asynchronous. Once you hand off work to it, you continue doing what you're supposed to do. In this case, I'm going to be waiting. Actually, block. This is a blocking wait. I will wait for this fence to, basically signal its readiness to me, is what I would call it. And by the way, all these errors that you're seeing, these are all just, temporary ones. This is a much better way to do error handling. This is just to make things a lot more simpler. Right. So once you're done with that, you go ahead and start reading. So if the GPU is returned and there's no issues with that, let me go ahead and read what I got back. That means whatever I wrote through that DMA transfer, whatever happened, did I get, did I write the right things? So I'm actually reading from GPU memory. There's a buffer somewhere over there of 1024 bytes. I'm going to be reading stuff back from there. And I'm basically using over here the time module to measure the amount of time that it took to write and come back and stuff like that. And then last time I didn't sort of speak to you about this. I didn't even include this. That's wrong. The last piece that you need to do is when you write this, um, because you're going to actually be dealing with Vulkan, you're in Rust, you're writing this in Rust, you're going to be talking to the C, the dynamic library that you're actually calling into, which is written in C. If you go ahead and simply assume that you just drop an item, for example, I don't know, which one is this? Device destroy fence. So I created a fence over here. All right. This is not a Rust object as such. This is an FFI object, technically, because this call is going to go ahead and allocate some space for this fence in, wherever in the vendor runtime that ultimately reaches out into user space, kernel driver, whatever it is. Okay. You've got to destroy that. So you actually have to go ahead and call destroy. And then you can't just rely on Rust's drop implementation, etc. Of course, we can go ahead and implement it ourselves. That means we can put all of the stuff that we intend to drop in a drop implementation. That means we have some state. We basically say struct, and then we hold the device and the fence and the buffers and all of that, and then say, okay, implement drop for that. That's a way you can do that. But it's not automatic like you normally see that in Rust. Right? So you do all of this, and then you basically get this. So the GPU took about 2.27 milliseconds, and I'm also measuring some more time of that. And then you see there is this repeating pattern, right? This pattern keeps repeating for 1024 times. So yeah, we're successfully able to allocate a buffer in GPU memory, transfer, or so the write 4 bytes, repeating patterns up to 1024 bytes, and then we're able to read that back as well, uh, and also cleanly, you know, deallocate all necessary resources that were allocated. All right. This is a simple workflow of, how you go ahead and put together a command, submit that command to the command queue, and then wait for the response that comes back. Obviously, this is just the beginning. This is just how we want to get the mental picture really, sort of really written down for yourselves. And this, I hope, will be has helped you with that, because this is certainly what I would have loved to have had when I started out. All this information is scattered around. When you start looking around for it, it's you'll feel like, yeah, I think this is possible. I think this is how it works, but nothing concrete. So I presume this is it. And yes, the last piece, if anybody's watched this and they know that there's actually something not quite right, please let me know, because this is something that took me a while to put together. But yeah, this is where we are. So yes, I believe that is what I would call the step about talking to your GPU. How do you actually talk to your GPU? And this is how you talk to your GPU. And then from here on out, you can start building more complex communication workflows, I can say. You can ask more complex work to be done and handle that complex work and do a lot of crazy things as well, as you will see. Right? So by now, I think one thing must be pretty clear. Just your writing this shader code, or the program that runs on the GPU, is just one part of the job, right? It's just one part of the job. All this stuff has to come together for you to be actually able to, really make your GPU work and get the results and the performance that you want, right? And that's what Vulkan is about. Yeah. So I guess that's about it. Did I miss anything else? Guess not. Okay. So yeah, took another hour. But yes, that's about it. So thank you very much. Have a good day.